Good afternoon. Good afternoon, ladies and gentlemen. Welcome to our session of the Nečas Seminar in Continuum Mechanics. Our speaker today is Professor Eduard Rohan from the University of West Bohemia in Pilsen, from the Department of Mechanics, and he will talk about homogenization-based model flow, piezoelectric porous metamaterials driven by peristaltic deformation.
Thank you very much for that kind introduction. It's really my pleasure to give the talk within this very distinguished seminar. After some years, I even don't remember where it was last time when I presented, maybe 10 years ago. So the topic of the talk is related to homogenization and the use of the homogenization to model a kind of metamaterial which is suitable for transporting fluid. So time is limited, so I will show the first slide. So what you see, the structure which you see is a periodic, and it consists of elastic parts, of electrodes, and of piezoelectric parts, which envelop porosity. So this bulged shape represents the pores filled with viscous fluid. Then it's surrounded by elastic material. Thank you. By elastic material, and then we have a piezoelectric material, the blue one, in which we have some electrodes, through which we can control this material. So basically, the idea is to propagate a wave of electric potential, which actuates on the piezoelectric material, and it causes a compression or just deformation in material. So it's called the peristaltic wave, which is propagated along the specimen. Of course, it's just to use the structure which is shown represents something quasi one-dimensional, but in general, of course, we are thinking about three-dimensional volume. And now the aim is to model such a structure which consists of many periods of such composite material. So of course, from the point of modeling and numerical modeling, it represents a problem which cannot be just treated directly. So the homogenization seems to be a suitable tool to provide a kind of effective model of such a material and to mimic the so-called pumping effect. So the pumping, as you can imagine, means that if we at the ends of the structure prescribe a pressure to the fluid which fills the pores. So if we have some overpressure, so for example here, if the pressure is larger than here, then pumping would be achieved if the fluid is transported against this pressure slope. And it appears that using the modeling based on the homogenization, if we capture nonlinearity, which is related to the deforming configurations, it can be achieved. So basically, these white points underneath represents the outline of the talk. So I will represent the homogenization of this kind of material. I will then account for description of the homogenized coefficient being dependent on the deformation, and I will illustrate how this kind of nonlinearity really works and why. So okay, I will go through some slides. I will almost skip some slides. So here I wanted to show that peristaltic motion can be based on the modeling. So this is the equation which we have, which we want to describe the peristaltic driven flow. So you can think about R as a radius. So radius is described by this bulge shape which is propagated, which is just shifted along a vessel, along the tube. This is by the way, this represents a model of the tube. And this is the equation for pressure, which is nonlinear. So it's of course with respect to pressure it's linear, but it bends the radius and displacements, so displacements of the vessel, and R is of course non-linear. But if you prescribe the shape of the channel, which is the bud shape which is moving along the vessel, so it's the equation describing the flow in such a vessel. Well, this can be derived based on some quite straightforward modeling. So mass conservation in tube, positive flow, based on this one-dimensional flow model. Then we integrate, we get the volume of the fluid, and substituting in this mass balance conservation, we get this equation. Well, I think I will move to the modeling of the piezoelectric material. So there are different options how to model the interaction between the piezoelectric and elastic material, depending on the scaling, which is a part of the homogenization. So as you know, so the microstructure is characterized by some characteristic length. Its proportion with respect to some macroscopic length is the scale parameter, which epsilon, and it is the matter of the asymptotic analysis of the system of partial differential equations. And now we can emphasize some effects by suitable scaling of some material parameters. So first I will show the case, so-called standard case, where there is no special scaling, and I will show what is the homogenized model of the piezoelectric porous material. So as for the constitutive laws which are involved in the model, so we have the elastic constitutive law here, supplemented by this part, which involves the gradient of electric potential. So this is the first part of the constitutive law, defining the stress through the elasticity and through the third order tensor of the piezoelectric coupling. The same tensor appears in the second equation, which is the equation for the electric displacement. And there is also the electricity. So the electricity is the second order tensor, again multiplied by the gradient of the electric potential. So this is the standard linear constitutive law describing piezoelectric material. I have to say that it's an approximation which works under some assumptions of small deformations, because normally we should retain a kind of hysteresis. But in many cases, the standard treatment is through such a linear constitutive law. Then we have the conservation law. So we have, of course, the divergence of stress equals some volume forces, and there are some volume forces, and we have the Gauss law saying that the divergence of the vector displacements equals the volume charge if there is some volume charge. So that's it, and we can proceed to the homogenization. So we need some periodic structure, and of course that there are heaps of papers on modeling piezoelectric composites nowadays. But the special things here is that we have interaction with fluid. So first I will show a simple interaction. Then we have one connected porosity filled with viscous fluid, which is not in this case, because we will first treat only quasi-static situation or static situation. So the viscosity is not most important here. So a part of these equations, which I already described, we have some boundary conditions and interface conditions. So those are very standard. So these are external boundary conditions. So we have some prescribed tractions. It's not important. We have some charge, surface charge, and on the interface we have, of course, the continuity of the pressure in the solid stress projection. So the tractions loading the solid part, they are equal to the pressure acting on the surface. The surface interface is denoted by gamma, and we have the insulated. We consider a neutral fluid, so there is the projection of electric displacement in zero on the interface. The coupling with the fluid is represented by this simple conservation, which just describes the extension of pores in response to the fluid injected into the porosity, and there can be also some effect of the compressibility of the fluid. So gamma is a compressibility of the material. So this is the mass conservation equation, which is only one equation because we have one connected porosity. So this is the weak formulation, and now we can so in this weak formulation you can see the presence of the pressure in the first equation, and we have this is the mass conservation equation. So now the homogenization can be applied quite straightforwardly. Normally we should get some a priori estimations, but we can also use the formal method of asymptotic expansion, which works very well. And it can be also modified by the use of the so-called unfolding operator method, which is very efficient. Yes, we can work with the peak formulation, and I'm showing here just very small concerning this method. So the unfolding operator enables to rewrite any function of variable x of the position x as a function of two variables of function of the x and y. So x is the coordinate in the heterogeneous structure, and it falls within one copy of cell of periodic cell. So we assume that the material is periodic, or the structure is periodic, and it's generated as a lattice of such cells. So if we have a position, so we get the lattice coordinate position, which can be this corner, and what remains from this point to x is called y. So this is the zoomed cell, which is used as the representative periodic cell. It's called y here in these equations. So this is the unfolding operator. Any function can be written as a function of x and y. It involves the scalar parameter, which is basically the size of this period. And important device is this integration formula, which says that the integral of function psi as a function of the coordinate within the heterogeneous structure can be represented through this unfolding as a function of two variables. And if we require the computations of this integral, so it's integral over the representative periodic cell y, or its subpart, and then integral over the global macroscopic domain. And third important thing is the unfolding of gradient. So if we have unfolding of a gradient, derivative of psi with respect to x, it's the same as the derivative of this unfolding function with respect to the so-called slow variable, fast variable, so it's y. So gradient with respect to y, and there is a factor 1 over epsilon. Now, concerning the asymptotic expansion, so in this case, we have no special scaling of the material parameters, so it's possible, it's the result of the a priori estimations. And such as the a priori estimation is such that we can use some recovery sequences of functions u epsilon, psi epsilon. So epsilon, the index epsilon just denotes that those functions are subject of the asymptotic analysis. So concerning displacement, we have the macroscopic displacement, so function depending only on x, and then we have this two-scale function u1, which is multiplied by epsilon. Yeah? So it depends on the macroscopic coordinate and microscopic one y. So this is error. There should be y as well, not t. There's no time so far involved. So sorry for this error. The same holds for the electric potential. Okay? Now, we take the weak formulation, we can inject these asymptotic expansions into the weak formulation, and we can just use the convergence results, which brings us to the limit problems. And when we test this, because we have this should be this number S, this symmetric gradient, so it's deformation, it's strain basically. And so this is the part of this strain associated with these virtual displacements or test displacements. So it should involve also this macroscopic part. But I'm now interested only in the local problem, so it's tested only by the fluctuating part of displacement, so by the two-scale function, depending on also on y. And similar in the equation describing this electric behavior, so this electric charge conservation, we test by this fluctuating test function of electric potential. And here we have this part associated with the stress. This is the effect of this of the electric field on generation of the stress. So, and on the right hand side we have the pressure. Pressure here, I recall that we are considering 1 porosity, so this is just a number. Well, now due to the linearity, I will go back. So due to the linearity, it's easy to see that these fluctuating parts of displacements of electric potential depend in some linear way on the macroscopic gradient of U, so macroscopic strain, and on the macroscopic field. So, and there is also the pressure acting on the surface of the pores. So we can define the fluctuating part of displacement and in analogy fluctuating part of the electric potential as these linear expansions involving some so-called characteristic responses or so-called corrector functions, corrector displacements with respect to the macroscopic strain, with respect to the macroscopic electric field, and with respect to the or pressure. And in analogy for the electric potential. So we have these three groups of so-called local problems, which I will present in terms of these bilinear forms. So we have the elastic bilinear form, then the bilinear form associated with these third order piezoelectric coupling coefficient, and in analogy with for the electricity. There is the effect, if I go back here, there is the effect of macroscopic gradient of macroscopic displacement, so the macroscopic strain, which generates a affine displacement at the level of the representative unit cell. So it can be expressed in terms of this tensor, which is basically linear function of the coordinate within this representative volume. Well, so those are the three local problems which I have mentioned. The first one provides the correction of the fluctuating part of displacements with respect to the macroscopic strain. So this is the problem for the displacement omega and for the electric potential theta, equipped with these two indices ij, which represent the strain, macroscopic strain mode. So in analogy, we have the effect of macroscopic electric field. So again, we compute this response, displacements and electric potential, where the index k represents the modes of the macroscopic electric field. And here we have the effect of the pressure. So there is only P. So in the right hand side, you can see that the structure is loaded by unit pressure on the pores. Here, this is just this piezoelectric response, where the driving, I would say the driving force here is this above mentioned macroscopic strain mode. So in some sense, the structure is pre-stretched, and we calculate the compensation of the macroscopic pre-stretch. Something similar here represented by the coordinate y. So I'm going a bit slow here because the same I will show later when I will deal with the controllable piezoelectric structure. Okay, so we will get this homogenized problem or two-scale problem. Well, so involving the fluctuating part of displacement, macroscopic displacement, again, the fluctuating part of potential, macroscopic potential. So I have already expressed the integrals over the microscopic cell in terms of the bilinear forms, which I defined before. And now regrouping all these terms which involve the test macroscopic strain and this macroscopic unknown strain, which is also involved in the expression of U1, we will get the elasticity coefficients and so on when coupling the pressure with the macroscopic test strain, we will get the Biot coefficient. So, and it's of course it is obtained upon substituting U1 and phi1 by this control L by these expressions, yeah. So then we will get these expressions for the homogenized effective elasticity of the material, for the Biot coefficient, and for the Biot compressibility. So those coefficients are standard in the Biot model. Normally we have only the back parts, but now when the material is extended for the piezoelectric material, so we have also the involvement of these dielectric coefficients of the piezoelectric coefficients at the micro level, and here the same. And moreover, we have more coefficients emerging with this electric charge conservation, so that we'll present this. Maybe I will go. Okay. I'll show here this effective constitutive law. So definition of the macroscopic stress in terms of the homogenized elasticity, homogenized piezoelectric coupling, Biot coefficient. And you see that in sense this constitutive law for the generalized constitutive law for the stress, for the electric displacements, and for the pressure retains some symmetry. This small j is an alternative to have possibility to inject some amount of fluid into the porous structure. Then, okay, so we could also eliminate the pressure from the structure, but this is just a technical point to define so-called undrained coefficients. So if you imagine that you have the porous structure with the pore and it is closed on the external surface, that you apply some electric potential on a part of the boundary, or you can cause some deformation. So due to the fact that the pressure is just one number within the whole structure, because we have 1.4, it can be simply eliminated, and you can define so-called undrained coefficients of elasticity of then you can have modified dielectric coefficients and modified piezoelectric coefficients. And in the end, you can see that depending on the pressure, if you apply some pressure in the pores, you can generate electric field, or if you inject some complementary relationship is for injection of the fluid, this red J, also generating the electric field. Well, we can also add the flow in the structure, but I will do it properly in the second part, which will be devoted to the controllable porous structures. So we already know what is the Biot model. I'm recalling the effective or the macroscopic model for the Biot-Darcy system. Here extended also for the inertial effects. So this is I would like to derive some analogical structure going from the micro level, from the heterogeneous structure, which is now equipped also by electrodes, which can be used to control locally the piezoelectric material. And at the beginning of the lecture, I have mentioned that it's important somehow to account also for nonlinearity, but the strategy of deriving homogenized model for such a structure, which would describe the pumping effect and which would describe the possibility to control such a material, really based on linear model, which then can be interpreted in a sense of some incremental formulation. Well, first I would like to illustrate. Oh, it runs surprisingly. On my computer it didn't run, so I'm surprised. Okay, so you can see the pumping effect. So we have some wave of propagating electric potential on these yellow and green electrodes, and it causes the deformation, the peristaltic deformation wave, and at the end it causes the flow through such a structure. Concerning the mathematical model, I would like to illustrate this behavior on a simplified or some reduced one-dimensional model. So we can think about two-dimensional structure, but because of some symmetry conditions, and I have to say now we will forget the dynamic inertia effects. So I will take the model which I'm going to derive. So I'm jumping at the end of the presentation. Yeah, but so I will get this expression for the macroscopic stress, which just retains the form which I showed before. The difference is that here we have some different coefficients, and phi is the control variable. The phi is the electric potential, so it's function of x and time, and it describes the wave propagating along this specimen. So I'm prescribing pressures at the end of the specimen. So if I take the difference of these pressures, I will get this stress at any cross section of such a structure. So I can eliminate the stress from this model. So I will get a model involving only the pressure. Yeah. So sorry, I not pressure, but I will eliminate displacement or the strain. Yeah. Due to the fact that I have no inertia involved in this model. So simply I will get this equation, and if I retain only the linear structure of the model, so I will have this is in particular the expression of permeability. So the permeability, which is computed for some specific structure, is the K0. Then I will add some other term to describe the sensitivity with respect to changing configuration. But if I forget it, I will get just this parabolic equation. Time derivative of pressure, and here I have the second spatial derivative of pressure, and this is the permeability. If I inject the formula which describes how the permeability changes with the deformation of the structure, so this in response to the pressure, to the strain, and also to the due to the piezoelectric effect, to directly the reaction on the electric potential, I will get these extra blue terms which make the problem nonlinear. Yeah, so this is the nonlinear PDE, and I recall that I want to describe the pumping effect. So prescribing pressure on. So, but yeah, well, okay. So this is the function. This is those colored curves correspond to the pressure distribution along the specimen for different times. I have the difference of the pressure between the left and right hand side. Right end of the specimen to 1 kilopascal. So, and I want to achieve the transport of fluid in this direction, so against the pressure slope. And if I consider the nonlinearity which I described just before, I will get the cumulative flux, which is increasing curve. Yeah, so it's okay, it pumps. If I don't account for this nonlinearity, I only have this kind of build model. There is no pumping effect. This is just the effect of the initial conditions, but then I have some fluctuations, so there is some motion to fluid there and back, but in general, if I integrate over some time, no effect. Yeah, so it's very important to account for this nonlinearity. So and there are some issues which I would like to face in the second part of the talk. So the nonlinearity, well, it will be sufficient to consider linear kinematics. Also, because if we think about the piezoelectric materials, typically the piezoelectric materials can be loaded only within the range of small deformations if we don't use some polymers which can be polarized and also provide such piezoelectric effect. So we will consider only linear kinematics. So linear piezoelectric constitutive flow, but it's important to somehow to respect the change of the configuration, especially if we speak about if we want to describe the shape of the pores and the fluid in the pores. So the reference configuration, so it can be considered as a homogenization of the balance equations prescribed in the deformed configuration. So therefore, I'm speaking about the homogenization applied at the Eulerian frame. As for the dynamic effects, so I will tell more in a minute. So we can also we can use the quasi-static model. Of course, it depends on the speed of propagation of this wave of the electric potential. So if this propagation is slow, because quasi-static model is sufficient. If you want to describe some faster propagation of such a wave, so we should account for inertia effects. And because we are also we describe the fluid flow in the core, so you know that there are some issues concerning this inertia in the Navier-Stokes equations. And then it's important to introduce a scaling in two respects. One is the well-known effect of the viscosity. If you want to homogenize Stokes flow to get the Darcy flow, because of the pressure profile, velocity profile in the force, it must be somehow reflected by the scaling of the viscosity. And another scaling appears in the scaling of the piezoelectric coefficients. This is the schematically the structure which we describe. So we have the white color is the fluid, then this blue are electrodes, and the brown is elastic or piezoelectric material. Concerning this nonlinearity, so going from nonlinear to linear, and then we will go back in some sense. So the modeling strategy is to start with the rate form or approximated rate form of the balance equations. This is in particular the balance of forces. So in the spatial configuration, so the stress is approximated by some current approximation and some quite recent reference configuration, quite recent spatial configuration, plus some fluctuation of displacement or perturbation of this of pressure of stress, pattern of stress, depending on the perturbation of displacement and perturbation of the electric potential. Then we have the well-known geometric effect. So this arises from the variation of the nonlinear part of the Green-Lagrange strain. Yeah. So this can be later on neglected, and then we have this effect of the fluid stress projection acting on the surface of the elastic material, and we have some boundary attractions. So I neglect this term arising from the variation of the Green-Lagrange strain. And so I get basically I get these equations. If I assume that in the recent deformed configuration, there is the equilibrium of forces and also there is conservation of the electric charge, I can obtain linear model for the increment of stress and in response to increment of displacement and increment of the earthly potential. So I will for this case I will derive the homogenized model. Then we should somehow be aware of how the things work. So basically, if we consider the sequence of the spatial configurations, so basically we are defining, in a sense, the hyperelastic constitutive flow. Yeah? So the stress is defined through the increments. So the aim is to get S is generalized state. You know? S involves the increment of displacement, or increment of stress, increment of state is the increment of displacement, increment of pressure, and increment of electric potential, which in this homogenized form will be just the control variable. Yes, so we define the increment of stress, and then the stress is, of course, with the integral over some paths of sequence of loading states. And then I equipped these homogenized coefficients by tilde, which means that these coefficients depend on the different configuration. So I consider certain different configuration, which is the heterogeneous structure. I apply the homogenization, which gives me some effective properties of the material. But then I will have to say, okay, but this was already for the different configuration. So it would be either recalculated at each new different configuration, or I can introduce some approximation based on the sensitivity analysis, and this will be the case. So this will be a strategy to model or reduction, which will enable me to get rid of this well-known effect of the finite element square computations. So you know that if you have two square problems, nonlinear problems, so normally you have to recalculate the response of all the microstructures involved to get locally the effective behavior of the material, which is needed in the global model of the homogenized structure. So then you can recalculate at the macroscopic level and go back to the micro level and so on. So it's very computationally demanding, usually almost impossible to use. So we seek for some strategies how to circumvent this effect. Okay, so I'm showing again the piezoelectric constitutive flow at the micro level. So I can now go very fast. The difference with respect to the case which I showed before is that I introduced the scaling. Scaling by epsilon of the piezoelectric coefficients and scaling by epsilon square of the dielectricity. And why is that? I will go right here. This is because if I have these electrodes, yellow and green, which are at the distance epsilon, basically, so the characteristic distance, characteristic scale is epsilon. When going down this epsilon, I am approaching the electrodes. So if I keep prescribe the both as a control variable, the potential at the green and yellow electrodes, I'm causing the exploding electric field. So it must be somehow compensated by the piezo coefficients. Yeah? Otherwise, I'm not able to get the a priori estimation simply. So there are two ways. Either I will do something with the control, so I will literally saying move the epsilon into the prescribed electric potential as a multiplier, or I will scale the coefficients in the constitutive flow. I choose the second option, and I just recall that we have also the scaling concerning the viscosity coefficients. Now, concerning the inertia effects. Well, so if we want to retain the inertia in the flow, so we have the local accelerations and we have also the effect of advection. So the message is that I will retain only the local acceleration. I will forget the effect of advection, but I could do it. If I did it, I would have to introduce two time scales. So this is the example of this is by the way for simplicity, let's consider just the static I mean the fixed force. So we have only the fluid described by W, which is the velocity. So this is the equation which should be homogenized. And if I forget this acceleration, so I consider only the static flow. So it leads to homogenization of this equation, keeping this advection term, leads to Forchheimer model, and it can be obtained by homogenization if I put some scaling in front of the expansion of the velocity, and I have the scaling of the viscosity, and the scaling is such that the beta is the coefficient, is the exponent of the scaling parameter in front of the viscosity. So beta plus alpha must be 2, and 2 alpha is 1. So a possible way to do it is to consider scaling of the viscosity by 1.5, of course, 1.5, and alpha would be 1/2. And for such a scaling, I can derive the Forchheimer law. Now for dynamics, if I want to also retain this local acceleration, something additional must be done. So to get the time in the game, because otherwise this term would just vanish. So the option is to introduce another time, so some fast time tau. So it's t over epsilon square of epsilon. Recalling that we have the scaling of the fast coordinate x over epsilon. And for this scaling, I can get the homogenized model. I will not use it later, but I'm just showing the complexity of the homogenization in this case. So then I have this partial derivative with respect to the fast time, which is tau. Here I have time derivative with respect to slow time, fast time. You see, so those two equations represent the mass conservation. So, for example, the velocity, which is the two-scale variable, appears only in this second equation, which involves the derivative of the pressure fluctuation with respect to fast time. It's not in this equation where I have only this time derivative of u. This u tilde is the fluctuation of displacements. Tilde means that I have the extension of the displacements into the pore. So it's like if you think about this AV formulation for computing fluid structure interaction, to have in some sense extends the displacement field into the fluid. So this is the tilde. Well, but I'm not going to describe the details because I will not use. So for now, I'm not. We are not interested in using such a complex model involving two times. So the way to get rid of this effect is just to neglect the advection term. So have to be non-stationary Stokes flow as a flow model. And for so this is the model which we are treating. So the equilibrium forces, conservation of the electric field, so of the electric charge, and we have this flow model which I've mentioned already, where sigma is the sigma f is the stress in the fluid part, involving the pressure, effect of the pressure, and effect of the viscosity. So I've already mentioned that I will use the decomposition of the fluid velocity into the relative velocity with respect to the solid extension of the solid velocity from the solid into the fluid. So this extension of the solid velocity is the u tilde, and w is the seepage velocity. And so I reconstruct the flows for the stress and for the electric displacements. I've mentioned the electric this definition of the pressure. So again, I have to skip some steps, and in the homogenization, we will inject the following expansions, truncated expansions of the displacement of electric potential, of the pressure, and of the fluid velocity. So the difference between this kind of the expansion and this one is the consequence of the scaling of the some sense these constitutive coefficients. So it would mean concerning the a priori estimation, it would mean that in this case we have the estimation of displacements and also of the gradients of displacements, while in the case of, for example, the velocity, we have only estimates on the epsilon multiple of the velocity, and in this case we have to estimate on the epsilon multiple of the electric potential. So then, due to the linearity, we have possibility to decompose the fluctuating part of displacement of this electric potential as functions of characteristic responses, which is the omega, ij, omega p, and omega k for the correction of macroscopic strain, correction of the macroscopic pressure, and correction of the electric potential, and similar for electric potential, and then for the velocity, fluid velocity, and fluid pressure fluctuations, we have only two correctors. So correctors with respect to the macroscopic pressure gradients. I will perhaps skip the details concerning the homogenization of the interface integral, which appears in one way. It appears in the balance of forces, because we have on the pore surface we have the loading of the elastic part by the fluid stress projected into the normal. And it also appears in the mass conservation equation. It's interesting to note and that even for the case of treatment of the inertial effects in the model, you get this interface integral. So basically describing the virtual work of the fluid stress on the pore surface, we get this expression involving only the pressure. So using the momentum equation momentum conservation in the fluid part, we can get rid of this viscous term, which appears normally as straightforward if we derive the convergence of this interface integral. We get appearance of this viscous effect of the viscous stress, but we can get through this local momentum conservation, we can get rid of this term, so we get at the end only presence of the macroscopic pressure. Okay? And in the dynamic case, we have also this presence of this, but it enters directly only the macroscopic equation, not seen at the local level. Well, so this is the structure of the two-scale homogenized limit of our system of equations, and so in some conventional way, I will distinguish the local problem to be solved, and I will get the local corrector functions, and I can present the macroscopic equations. Some remarks concerning. Do I have still some time? How we are?
You can run to 45.
45? Yeah, okay. So I will speed up. So basically, the procedure which I showed before, it repeats. So I will get the structure of the local problems to be solved in the solid part. So it's not too much of interest. Yeah? It has to be done, but it's not too much of interest. What is more interesting is the question concerning the fluid flow. So one option is to compute the spectral response of the flow. So I can, by computing the eigenvalue problems, I can get the system of eigenvelocities to say omega r and correspondingly eigen numbers. And I can define the seepage flow two-scale function. So it depends on time, on microscopic variable, also on the macroscopic coordinate. I can get it as an expansion with respect to these eigen functions. So this just illustrates some modes, some eigen functions in the pore. And then I can solve this simple ordinary differential equation for the coefficient alpha r, which is the weight of this particular eigenfunction, of course. And then it allows me to express, so I get this solution for alpha. Yeah, so it involves some convolution. So normally, of course, the convolution kernel is given by the particular eigen number. And then there's the difference between the integral variable s and the time at which we want to evaluate, at which we want to evaluate this function. Yeah? Later on, I would like to introduce the small linearity. So it will appear that I need to solve, I need to imagine, at least imagine that I'm solving this eigenvalue problem at different times. Yeah? So the eigenfunctions and eigennumbers will depend on the different configuration. So it will depend, in a sense, on time. And if I evaluate, again, I will skip some details, but if I evaluate the dynamic permeability, I get this expression, but I equipped the eigenfunctions and eigennumbers with this lower index T or S, which is the meaning of time. Yeah. So concerning this convolution kernel, so the permeability, which appears as a convolution kernel, it's non-symmetric. So it depends on T and S. So normally, if I'm linear situation, if I have a situation of undeformed configuration or non-deforming configuration, I get the symmetric expression of the permeability, of course. But as the matter of fact of the deformation of the pores, I get this non-symmetry in this expression. Well, there is some issue concerning the time discretization. It's not so much of interest, and I have already spoken about the solving these problems in the solid part for the corrector functions. So in the end, I'm able to define the homogenized coefficient, or to calculate the homogenized coefficients of elasticity, Biot coefficients, the compressibility, and also some coefficients related to the control by the electric potential. So this is the second order tensor H and coefficient Z, and I have the permeability, which is the static permeability, but for the case of involvement of the inertial effects, I get the dynamic permeability through this. So the seepage velocity is defined through this convolution. And now, so I will skip this, but now how to get the nonlinearity in the model. So I mentioned that I'm deriving the homogenized model for a certain state of deformation. I got the linearized formulation, so I have a linear model, I get the linear model as the homogenized model. But now I forget I try to recall that I'm working in the different configuration, so it must be somehow respected. So if you start with such a configuration, such a representative periodic cell, after deformation, it attains this deformed shape. So you can have the pore and some matrix, and this is just the effect of the displacement. Yeah? And the fluctuating part of displacement, it appears on the macroscopic strain, on the pressure, and on the control variable. All is involved. So, and the strategy is to avoid the need of recalculating with each new configuration to solve again these local problems, to try to estimate or approximate the correctors, the local responses, and at the end to estimate the homogenized coefficients. So for this, the sensitivity analysis, which is normally used in the shape optimization, is a suitable tool. So that's it. So for any coefficient H in general, depending on the configuration, on the deformed configuration, I can get this linear expansion. So H0 is just the homogenized coefficients computed at the initial intact state of the configuration, and then this perturbed shape, the effect of change of these coefficients with the change of deformation is captured by this linear part. So I compute this derivative of the homogenized coefficient with respect to macroscopic strain, with respect to macroscopic pressure and the control variable. And again, I repeat that the means to do it is to use this scientific analysis, which is normally used in the shape optimization. So it means that I need to, well, I think it's not necessary to discuss details, just for illustration. So if I want to derive the sensitivity of the permeability, which is the crucial parameter in the model, by the way. So I get such an expression involving this V, which is the so-called design velocity field. And this design velocity is given by the microscopic displacement. So when if I compute the macroscopic response, I could reconstruct the microscopic displacements, and I could compute this differential of the permeability, but I want to do it before the computing. So it means that in the place of this design velocity, I can consider, this corrector function. So because this is the displacement, which appears as the weight of the applied macroscopic strain. This is the displacement, which appears as the weight of the applied pressure. Yeah. Okay, so I wanted to mention some more about the relationship with respect to in the context of this going from the linear formulation back to the nonlinear. So at least I would like to mention this. So I can somehow summarize the homogenized model, which can be presented in this form of the residual. So my macroscopic variables, which emerge from the homogenization, is only the displacement and the pressure. So basically, my equation is psi equals 0, where the psi is residual, given by the stress, macroscopic stress, and by the other expressions. So this is the Darcy flow. This is the force equilibrium, and this is the mass conservation. There is also the control variable, the electric potential involved. This triangle means that this is this. So U minus U triangle means the approximation of the time derivative. Yeah, so I'm working with some time step. Time step delta T appears here. So it's a semi-discretized formulation in time. So I want to resolve this equation, but as the effect of dependence of the homogenized coefficients, elasticity is somehow embedded in this definition of sigma, but the other coefficients B, M, Z, and this permeability K. So I have a nonlinear problem to solve. Yeah? So the way to solve it is to use kind of Newton method. So I have to get the differential of this residual function. So I'm differentiating of the homogeneous coefficients, and this is where I'm using the sensitivity analysis. Yeah. So this is the natural way how the sensitivity appears in the macroscopic homogenized problem. So, for example, if I'm injecting this formula for the linear expansion for the permeability in this expression appearing in the homogenized equation, so I get all this, and based on if I somehow regroup the coefficients which corresponds to which combine. So it's very technical, so I skip many details, but of course, that if you differentiate, for example, the elasticity, you will get not only the dependence on the strain, but also on the pressure. So it combines them with the Biot coefficient and so on. So it's just a mixture of, and so it leads basically just to illustrate that, for example, here I have something like elasticity, a bar elasticity, but it depends on the primary obtained homogenized elasticity plus the effect of the differentiation. And you can also have the differentiation of the Biot coupling coefficient, so it's a bit complex. Yeah. So finally, I will skip this, and I think it would be good to end with some examples. Just a minute, and so I will now consider this quasi one-dimensional problem, but based on the three-dimensional calculation. So I have three-dimensional structure, three-dimensional pores, and also this macroscopic specimen, this model is a three-dimensional body. But of course, the problem is such that it leads to something which is quasi one-dimensional. So I can display the solution along some lines which leads to the specimen in the x direction. So this is the distribution of the pressure at different time instance, and I combine the homogenized model with the response of the direct numerical simulation. So I have the non-homogenized problem with all the periods. I run the numerical computations, which provides this blue curve, and I compare with this yellow curve, which is the result of the nonlinear homogenized model. So there is some discrepancy in the pressure, the displacement, but the match is much more better. I can reconstruct the flow at the microscopic level. And now concerning the pumping effect. So if I forget this nonlinearity, I just consider the initial configuration, I do the homogenization. So there is no pumping effect. Q is the cumulative flux. It's computed in straightforward way. It's the time integral of the fluid velocity over some cross-section. So there is no increase of this curve. If I apply the nonlinearity, which I try to describe, I get some pumping effect. There is also dependence on the pore shape. So if you just you try to use different pore shapes, so so we use this kind of pore, this bulge like lemon shape of the pore. Then you can think also about just the straight tube. Why not? It's usually people ask why not to use just a straight tube. Yeah. So you can do it, and then it also depends on the size effect. So if you consider the thicker tube or thinner tube, it matters. So for this thick tube, the curve decreases, which means that there is no pumping effect. This is just pad tube, Darcy flow, passive Darcy flow through the structure. Because of this, or due to this excitation, due to the actuation of the piezoelectric material, there are some waves, this phase wave. So this is different times you can have more or less, but the curve decreases, so there is the opposite flux than the desired one. If you consider narrow pores, there is some very slight pumping effect, and if you use this bulged shape of the pore, it's much better. Some effect of the inertia, but well, okay, I will. Maybe you go. Yes, it works. So this is another case where we are thinking about this structure, because you can consider something like some plate structure where the structure of the elastic material and pores is distributed in such a way that you have the connected pores in two directions. So this is just connected porous structure in a plate or in a plane. And you have these control handles, these electrodes. So you can by some boundary conditions, you can steer, you can control the propagation of the wave of electric potential to the structure, and it enables you to somehow to direct or to change the direction of the fluid flow through the structure. So including the pumping effect, and this is what I wanted to here to simulate. Yeah. I think this I will have. Thank you very much for your attention.